That split-second reaction you see when you pause a video relies on a highly organized, hyper-fast restaurant kitchen working behind the scenes. At the center of this kitchen is the head chef, known as the processor or CPU. The chef is incredibly fast, but they only have two hands and can't store any information in their own head. It's the data and instructions. Finally, the waitstaff represents input and output components, or I/O. They bring in external orders, like a mouse click, and deliver the final dishes. This diagram shows the flowchart linking these three roles. Everything in a computer works through this continuous, synchronized loop between the chef, the recipe book, and the waiters. There is one strict rule for this kitchen. Despite the chef's speed, they have extreme tunnel vision and can only execute exactly one recipe step at a time, strictly in order. This is John von Neumann, the mathematician who created this rule. We call this specific way of organizing a computer the von Neumann architecture. Restricting the chef to one task at a time is actually a strength. Enforcing this sequential order prevents chaos and guarantees complex programs are resolved predictably every single time. Let's watch the chef work. First, they look away from the cutting board to read the next step in the recipe book. This first move is an instruction fetch. Next, the chef grabs the ingredient and performs the requested action, like chopping a carrot. This is the execute phase. This constant back and forth, looking at the book, then chopping, is the core heartbeat of the machine, known as the instruction cycle. This diagram shows the specific states of an instruction cycle. Engineers divide the cycle into microtasks, like instruction address calculation to find the page and instruction operation decoding to choose a tool. A computer's power comes from its ability to run this exact fetch-execute loop billions of times every second. However, this leads to a problem. Imagine the chef puts a turkey in the oven. This represents a slow process, like downloading a large file or waiting for a human to type a key. If the ultra-fast chef just stands there idle, staring at the oven for hours, the entire kitchen freezes and the system's efficiency drops to zero. The solution is an oven timer. The chef immediately starts making a salad, and the oven yells beep when the turkey is ready. We call that beep an interrupt. This flowchart outlines the basic interrupt flow. When the processor receives the signal, it pauses, saves its place, handles the new request, and returns to work. This restore and resume step acts like a bookmark in the recipe, ensuring the chef doesn't forget the salad. Interrupts are the fundamental trick that allows computers to multitask seamlessly without wasting time on slow physical devices. To keep up with the chef's speed, ingredients have to travel incredibly fast between the countertops and the waiters. We call these paths the system bus. A single path would cause a massive traffic jam, so modern computers use multiple lanes to transmit data in parallel. This diagram illustrates a multi-lane distribution system. Large packets of information are split apart, sent simultaneously down these parallel physical lanes, and reassembled at their destination to maximize speed. Even the world's fastest processor is useless if this interconnection structure cannot feed it data fast enough. Now that we understand the kitchen, we can look at the physical interior of your device. Those distinct physical chips on this motherboard are the real-life chef and the recipe books, your processor and your memory modules. These literal gold lines painted onto the board are the conveyor belts and multi-lane buses we just talked about. Technical terms like instruction cycles, I/O modules, or hardware interrupts simply describe how electricity physically flows through the circuit board. A computer is an incredibly well-organized kitchen, perfectly designed to cook billions of math problems every single second.